Learn like a pro.
Hey there and welcome. Have you ever stopped to think about what the fuel in your car, the plastic in your phone, and even you are actually made of? Well, the answer is all around us, and it's called organic chemistry. But hey, don't let that name scare you off. We're going to see that it's really just like playing with the universe's most amazing Lego set. So let's get into it and start building.
So, I've got a question for you. What on earth do Legos and gasoline have in common? Well, it's simple, really. They're both built from these basic repeating little units that you can snap together in like a million different ways to create something way more complex. And that's the big idea we're going to be playing with today.
All right, here's our game plan. First, we'll check out our basic bricks. Then, we'll meet the simplest family of molecules you can make. After that, we'll see how to build different shapes with the same bricks, learn the secret code for naming them, and finally see what kind of cool stuff we can do once we've built our creations.
Okay, first up, carbon's chemical Legos. You know, organic chemistry, when you boil it all down, is pretty much the study of one single element, carbon. It's so incredibly versatile that it forms the backbone of literally millions of different compounds that make up, well, everything. And the simplest of these carbon compounds, our most basic fundamental Lego bricks, are made of just two things, carbon and hydrogen. That's it. We call them hydrocarbons, and they are the absolute foundation for everything we're about to build.
So, let's kick off our first building project and meet the alkane family. These guys are the simplest, most straightforward structures you can possibly put together with those carbon and hydrogen bricks of ours.
Now, alkanes are what chemists call a homologous series. The easiest way to think about it is like a family. All the siblings look kind of similar, they share the same family rules, but each one is just a little bit bigger than the one before it. Same basic plan, just with a few more pieces added on each time. Okay, check out this family portrait. These are the first four alkane siblings, and I bet you've heard of them. You've got methane, that's your natural gas, ethane, propane for the barbecue, and butane for lighters. See the pattern? Each one just adds one more carbon and two more hydrogens. And look at their boiling points. As the molecules get bigger, it takes a lot more heat to get them to boil. Super logical, right?
All right, this is a really important idea. It's the difference between having a parts list and having the actual building instructions. A molecular formula like C4H10, that's just your list of parts. It tells you, hey, you've got 4 carbons and 10 hydrogens. But the structural formula, that's the blueprint. It shows you exactly how every single one of those pieces snaps together.
And as these alkane molecules get bigger and bigger, their whole personality changes. We already saw their boiling points go up, but they also get more viscous, thicker, like going from water to honey. And kind of surprisingly, they actually become less flammable. Think about it. Tiny methane is a super flammable gas, but a really big alkane might be a thick wax, which is way harder to light on fire.
Okay, so what happens if you take the exact same pile of Legos, but you snap them together in a totally different way? That brings us to our next big idea. Same bricks, different shapes. Or, as chemists call them, isomers.
And this is where that whole Lego analogy just fits perfectly. Isomers have the exact same parts list, the same molecular formula, but they have a completely different blueprint, a different structural formula. Same parts, totally different creation. And believe me, this is a huge deal, because isomers can act completely differently from each other. Let's take a look at a classic example, butane. The parts list for both of these molecules you see here is C4H10. On the top, you can see all 4 carbon atoms are just linked up in a nice straight line. But on the bottom, we took one of those carbons and snapped it onto the middle one, creating a little branch. See? Same parts, totally different shape.
And that's really the key difference that creates isomers with these alkanes. You can have a straight chain where all the carbons are just in a single row, or you can have a branch chain where one or more of those carbons juts off from the main line, kind of like a branch on a tree.
So if we can build all these different shapes, we're definitely going to need a way to tell them apart, right? We need a system. It's time to learn how to read the naming blueprint.
Now, I know this might look a little intimidating, but trust me, it's just a simple 3-step recipe. First, you find the longest running chain of carbons. That gives you the molecule's last name. Second, you spot any branches that are sticking off it. And third, you just number the main chain so that your branches get the lowest possible address. That's it.
Okay, let's try it with this one right here. Step 1, what's the longest chain? Let's see, 1, 2, 3, 4, 5 carbons. So its last name is pentane. Easy. Step 2, what's the branch? It's just a single little carbon group, which we call a methyl group. And finally, step 3, we number the chain. If we count from the left, that branch is on carbon number 2. If we count from the right, it would be on number 4. The rule is, always go with the lowest number. So put it all together, this is 2-methylpentane. See, the name is the blueprint.
All right, so now we're basically pros at building and naming these things. But what can we actually do with them? It's time for the fun part, making and breaking our creations. Let's talk about the reactions of alkanes.
Alkanes are called saturated. All that means is that their carbon atoms are holding on to as many hydrogen atoms as they possibly can. They're full. This makes them pretty stable, maybe even a little boring and unreactive. But they are fantastic at 2 very important things.
The first one is combustion, or, burning. If you have plenty of oxygen, you get what's called complete combustion. It's super efficient and it produces carbon dioxide and water. That's the nice, clean blue flame on your gas stove. But if you don't have enough oxygen, you get a nasty, smoky yellow flame. That's incomplete combustion, and it produces soot and that really dangerous gas, carbon monoxide.
Now, the other key reaction is a little more subtle. It's called substitution. Instead of just blowing the whole molecule apart by burning it, we can just swap out one of its little hydrogen atoms for something else, like a chlorine atom. To get this to happen, we just need to give it a little kick of energy, usually from something like ultraviolet light.
Okay, so watch what happens here. We start with our simple little methane molecule and a chlorine molecule. The UV light comes in and gives it a little zap of energy, and bam! One of the hydrogen atoms on the methane swaps places with a chlorine atom. And just like that, we've made a brand new molecule, chloromethane. And it doesn't just stop there. This reaction can actually keep going, swapping out the second hydrogen and the third and even the fourth hydrogen for chlorine atoms. This is how chemists can take a really simple starting material and, step by step, turn it into a whole bunch of new chemicals with all sorts of new uses.
So there you have it. We've seen how just 2 simple elements, carbon and hydrogen, can act like the ultimate Lego set. We can build entire families of molecules, create totally different shapes from the exact same pile of bricks, and even swap out pieces to invent new things. We've basically learned the fundamental blueprint. So the only question left is, what else could you build?